Okay, let's discuss the few notes that actually come after this little video. The first is that when we said the 2x2 determinant was the area of a parallelogram. And the example we did, we started with something like 5, 2, and then 3, 7. And when we drew those, 5, 2 was over here. At least the point 5, 2 was. The vector 3, 7 ends up like this over here. The parallelogram we drew looked like this. It looks like this. And when we found the determinant, we said it was the area of that parallelogram. And we found ourselves calculating the usual determinant formula, which is fine. It is great. However, let's just switch to two columns. And I'm going to write 3, 7 and 5, 2 like that. Unfortunately, the parallelogram I draw is exactly the same one. But the formula gives me 3 times 2 minus 5 times 7. That's negative. Now, how can I possibly say that the determinant of a 2x2 is defined to be the area? Well, what it's defined to be is the signed area. You have seen signed area before. For example, when you were doing integrals in Calc 1, and someone said, let's look at the integral signed from 0 to 2 pi, we call the area up here positive area, we call the area down here negative area. What we're really saying is that the integral was this area with a plus sign in front of it plus this area with a minus sign in front of it. So we have seen signed area before. You have seen signed distances before, because that's all negative and positive numbers actually are. Back to determinants though, what does the sign mean here? Well, it's going to turn out, and it's not that hard to show, that if I get a positive number for the determinant, that's going to mean that as you can rotate the first vector in a counterclockwise direction until you hit the second vector. So the direction would be counterclockwise. That's not what happens here. If I start with the first vector and start rotating, I'm going to have to rotate it this way, which is clockwise. So the size of the determinant of a 2x2 determinant will always be the area of a parallelogram. The sign will be positive if you rotate the first vector counterclockwise to hit the second vector. The determinant will be negative if you rotate the first vector in a clockwise direction and hit the second vector. So it does have a lot of orientation information there as well. Finally, when you took linear algebra, and this does come into play here in a day or two, if I look at a matrix, it's possible for the determinant to be 0. And I think the algebra to actually show what's going on there is kind of hard, but the geometry is easy. So let's just think about the geometry. In order for us to get a parallelogram whose area is 0, the only way you can do that is if you draw vector AC, it looks like that, and they get no area, BD has to lie in the same line, like that. It's the only way possible. Now that means the vector BD has to be a multiple of the vector AC. So we can only get 0 if the matrix actually looks like some column, and then the second column is just a multiple of the first column. That comes straight from the picture. Showing that algebraically is kind of hard, but we can get 0 determinants, but that's only when the area of the parallelogram is 0.